So, students, a very good evening to all of you. Today, I am here with you one more video that is related to the design of synchronous machine. In this video, we are discussing about the output equation of a synchronous machine and on which factors this output equation depends. Moreover, we are also dealing the factors which are dependent upon this output equation. By changing these factors, how the output equation can change. Now, before discussing the output equation of a synchronous machine, as we all know, for design point of view, whether we have to design the generator, the transformer, the motor, we have required a certain guideline. And the output equation is one of the guideline that helps us to determine the main dimensions that includes the diameter as well as length of the armature. It includes the armature design, which comprises of stator slots, conductors per slot, total number of conductors, resistance of the winding, and many more. Now, before discussing about the output equation of a synchronous machine, first of all, we have to know that what is this synchronous machine? So, a synchronous machine is a machine that consists of both a generator as well as a motor. As you all know, construction wise there is no difference between a generator and a motor, but only difference is that thing, their principle of action. So if you can say that a machine which converts the mechanical energy into AC electrical energy, then it is called as a generator. And if the same machine is operated as a motor, then it is called as a synchronous machine. One of the most important thing that you should kept in mind in case of a synchronous machine, that a synchronous machine is an AC machine whose satisfactory operation depends upon the main factor. And the main factor is, in case of synchronous speed, your synchronous speed, that is ns, is equals to 120 f by p, where f is the frequency and p is the number of poles. Now, we have to calculate its main dimensions, its armature design, and many more. So for that thing, we have to discuss its output equation. Now, in this, you can say that video, I will tell you how the output equation of a machine can be calculated. As you've seen on your screen that the output equation consists of the following terminologies, and moreover, these terminologies can be used in case of a synchronous machine, where we have VPH is the phase voltage, ZPH is number of conductors per phase, NS is synchronous speed, P is number of poles, phi is flux, KW, that is a winding factor, it is a constant value having value 0.955, L is gross core length, C naught is output coefficient, IPH current per phase, TPH number of turns per phase, NS synchronous speed, that speed is in RPS, and we have to calculate this speed, we have to convert speed into RPS. AC specific magnetic loading, and BAV average flux density, and last will be D is the diameter of the stator. So these are the terminologies we can use in whole of the design of a synchronous machine. Now, in case of a synchronous machine, let us suppose we have a three-phase generator. Now, in case of a three-phase generator, the output of the machine is given as Q is equals to 3 VPH IPH into 10 to the power minus 3, where VPH is phase voltage, IPH is phase current. Let us assume this VPH is equals to EPH. Then your above equation becomes Q is equals to 3 EPH IPH into 10 to the power minus 3. We know that in case of a synchronous machine, the induced EMF, that is EPH, is equals to 4.44 into F into phi into TPH into KW. Now we have to convert this TPH, that is turns per phase, in conductors per phase. So for that thing, you have the equation that is 2.22 F into phi into ZPH into KW. That is, your ZPH is basically equals to TPH upon 2. Is it clear? Now, as we also know that the frequency of generated EMF F is equals to P NS upon 120, or it is P NS upon 2. The first figure will be when the speed is in RPM, and second figure is when the speed is in RPS. Now substituting these values in the equation Q 3 EPH IPH into 10 to the power minus 3. So you have this equation. The first term, that is P phi is equals to BAV pi dl, is the equation for specific magnetic loading. And the second equation, that is 3 IPH ZPH upon pi d is equal to AC, is the equation of specific electrical loading. Now substitute the value of specific magnetic loading and electrical loading. We are getting Q is equals to 11 BAV AC KW into 10 to the power minus 3 D square L into NS. Now this 11 into BAV AC KW 10 raised to power 3 is basically known as output coefficient. So your equation becomes Q is equals to C naught D square L into NS, where C naught is called as the output coefficient. So this output equation can be used to calculate the main dimensions as well as the armature design, the resistance of the winding, and all those. I think this is clear to all of you. Now, you see, in this output equation, your output is largely dependent upon the two main values, that is BAV and AC, whereas your KW value is a constant value. So this BAV and AC is known as specific magnetic loading and specific electrical loading. So by changing the value of BAV and AC, you can change the value of output coefficient, and once the output coefficient will change, your ultimately whole of the equation will change. Now, in the next slide, we are discussing what are the various factors that affects the choice of specific magnetic loading and the choice of specific electrical loading. Now, here we have the choice of specific magnetic loading. The specific magnetic loading, that is BAV, which is equals to P phi upon pi dl, is dependent upon these main factors, that is iron loss, voltage, transient short circuit current, stability, parallel operation. So these are the total 5 points on which the specific magnetic loading will change. We can change the value of one of these factors, the specific magnetic loading will change, and vice versa. For numerical point of view, this value of specific magnetic loading is lies between 0.50 to 0.65 Weber per meter square, which is categorized into two main components. Number one, if a machine is having a cylindrical rotor, then it will be 0.55 to 0.65. And if the machine is salient pole, then it will be 0.50 to 0.65. And mind it, this is the value that we can't assume in a circuit. This value will be given to us for calculation of the main dimension and all that. I think it is clear to all of you. So this is the one thing, that specific magnetic loading is dependent upon these 5 number of factors. And if we change the number of 5 factor continuously, your output will change. Now in the next slide, we have specific electrical loading, that is AC, which is equals to IZ into Z upon pi d. And moreover, this specific electrical loading is also dependent upon the number of factors like copper loss, voltage, synchronous reactance, straight loss. So you can say that again, by changing these 1, 2, 3, 4 categories, you can change the specific electrical loading. And once this specific electrical loading can change, your output is also changed. It is just similar like to your specific magnetic loading. Now, as you are seeing, specific magnetic loading value lies between 0.50 to 0.65. In the same way, specific electrical loading values also lies between 20,000 to 1 lakh, that dependent upon which type of rotor you can use. For example, if you use a turbo machine, then the value of specific electrical loading is 50,000 to 1 lakh. And if you see silent pole machine, then you have 20,000 to 50,000 ampere conductors per meter. So these are the two main factors which will greatly affect the output coefficient, and this output coefficient is dependent upon your main equation of synchronous machine. One more thing, the output equation in having a value kW, and this kW is a constant value. Now I think it is a clear to all of you about the output equation. Now in the next video I will come with you, once you can calculate the output equation, your output coefficient, this output coefficient when you relate with the output value of the machine, you are getting a value D and L. So in the next video, I can tell you about how you can separate the D and L. That is how you can separate the armature diameter and stator core length. So for that thing, you have generally adopted the two things. So before going to that particular topic, first of all, you go to this video, you go through this output equation, and once this output equation will be clear to all of you, then it will be quite beneficial for you. Is it clear to all of you? So we will meet you on another video where we have to separate the D as well as L. I think this video is all clear to all of you. So we will we will meet you in the next session also. Thank you so much.